Hey everybody, Dr. A here, and in this video we are going to be exploring a third example of applying LRFD load combinations. So let's jump in and take a look at the given information. So we are being asked to determine the factored maximum shear force, bending moment, and axial force in member AB in the frame shown here using LRFD. So we're being asked for really three things regarding member AB. So let's take a look at this frame and make sure we know what we're looking at. We have this two-member frame. Member AB is the vertical member, and then member BC is this horizontal member. The frame is being supported by a pin down here at A and a roller at C. So along the top member, BC, we have it supporting a uniformly distributed dead load, WD, of 1 KLF, and a uniformly distributed live load, WL, of 1.5 KLF. And then along the vertical member AB, we have a uniformly distributed wind load of 0.5 KLF. And then, of course, we have our dimension lines. AB is 12 feet long, and then BC is 10 feet long. So let's go ahead and see how we can get this problem started. So what I like to do after I write solution is I like to perform an analysis on this frame only exposed to each of the service loads one by one. So what I'm going to do is I'm going to start with a dead load analysis. So I'm going to redraw this frame only supporting the dead load, not including live and wind, and only supporting the dead load. I'm going to determine the shear force, bending moment, and axial force in member AB. Then I'm going to perform a live load analysis, follow the same process. Then I'm going to perform a wind load analysis, again following a similar process. So we're going to end up analyzing this frame 3 times. Once only exposed to dead load, a second time only exposed to live load, a third time only exposed to wind load. Then after we collect the service load analyses results for each type of service load, then we will investigate which load combinations are applicable and then apply them. Okay, so let's go ahead and start with our dead load analysis. So I can go ahead and redraw this frame. Here's A, here's B, here's C. Of course, this is giving us 12 feet. Horizontal length is 10 feet. And then only exposing it to the dead load, we have our dead load analysis diagram looking kind of like this. And that dead load, WD, is 1 KLF. So pretty simple at this point. What we're going to do is we're going to compute the shear force, bending moment, and axial force in AB due to the dead load alone at this step. Now, you may be looking at this and you may be saying, oh, wow, it's pretty simple. It's almost trivial, and you're right. So let's go ahead and I'm going to superimpose a free body diagram on my dead load diagram. So, of course, I have an AY here, and I have an AX here, and then I have a CY here. So obviously, just looking at this, if you look at the entire diagram here, if you say sum of the forces in the x direction equals 0, we see immediately AX equals 0. Now, because AX equals 0, if you think of like a method of sections operation, AB is not going to be exposed to any shear or moment. Okay, so we can then say V, the shear in AB and the moment in AB are both 0. Okay, so as a frame only exposed to dead load, AB is only serving as a pure compression member. Okay, AB is a pure compression member while only supporting the dead load. And not only that, but it's pretty symmetrically placed. So maybe pause the video and you go ahead and punch this through, but you can hopefully tell that by symmetry, AY equals CY equals what? Equals 1 KLF times 10 feet divided by 2. And so you get that as 5 kips reacting upwards. And so the axial load in AB is going to be equal to 5 kips in compression. So again, if you maybe pause the video and think about it for a second to convince yourself of it, because I'm not going to show every single detail in this video. I'm assuming you're already kind of comfortable with these equilibrium procedures, but AB would be a pure compression member in exposed to 5 kips in compression for this loading scenario. So that's our dead load analysis. Now, similarly, we're going to do a live load analysis. Now, you may be thinking that's going to be very similar to the dead load analysis. So without showing a whole lot of extra work, I'm going to make a note of that. I'm going to say this is similar to the dead load analysis, but the frame is only supporting W live equals 1.5 KLF. So if you want to, you can redraw this frame, but showing W live here. But it's going to, geometrically, it's going to look exactly the same as your dead load analysis. Only difference is you have 1.5 KLF and it's called W live. So from your live load analysis, you'll come to the conclusion that the shear and moment in AB are 0 in the live load analysis, and your AY equals CY equals 7.5 kips reacting upwards, and that's going to give you an axial force in AB. Give you an axial force in AB equaling 7.5 kips in compression. So this is an upwards arrow, by the way, here. So that's our live load analysis. Now, again, we're going to do a third analysis. It's going to be our wind load analysis. Now, this one is going to be a little different. We need to redraw a diagram for our wind load analysis. Okay, so we're going to say wind analysis. And again, we're going to redraw our frame, but only exposed to the wind load. So this geometrically is gonna, the loading is oriented differently than it was for our dead load and live load analysis. That's why we're redrawing this one, okay? And we're exposing this member AB to 0.5 KLF, and of course, member AB is 12 feet tall. Member BC is 10 feet long, and we can put our labels here just to remind ourselves what we're looking at. Again, I'll superimpose a free body diagram on this. We have an AY, we have an AX, and then of course we have a CY. Okay. And so ignore that notification that just popped up there. What we can do now is apply equilibrium equations to solve for these reactions. Okay, so clearly we can say sum of the forces in the x direction equals 0. And when we do that, we'll come to the conclusion that AX equals 6 kips pointing to the left. Again, I'm kind of skipping some of my equilibrium steps because you should be comfortable with that by this stage of your academic career. Next, I'm going to say sum of the moments about A equals 0 counterclockwise positive. And, of course, we can say negative 0.5 KLF times 12 feet times 6 feet. And then plus CY times 10 feet equals 0, and we will calculate a CY as 3.6 kips pointing up. And then by summing forces in the y direction and setting it equal to 0, we will get an AY is 3.6 kips going down. Now, what does that mean when we have 3.6 kips going down? Well, this is going to indicate that our axial force in AB is going to be 3.6 kips in tension, not compression this time. So let's draw a couple of follow-up diagrams to help us visualize this some more. So let's look at the shear diagram for AB. Okay, so if we look at the shear diagram for AB, we're going to have maybe an x-axis here, and we can call positive shear axis here, and this is of course going to have units of kips and feet. And our shear diagram, we're going to interact with AX first. So AX is going to be pushed to this point right here, which is 6. And then we're exposed to a uniform distributed load. So that 6 is going to, that shear diagram is going to decrease at a rate of 0.5 KLF until we get just underneath this corner of the frame here. And so we're going to have a shear diagram that looks like this. Let me draw it a little bit better. Looks like this, and this is, you know, at the 12 feet mark. And of course, this is going to be a linear shear diagram, okay? And then this is wind, so I can put a little W subscript there, V sub W for shear due to wind, okay? And then let's go ahead and sketch the moment diagram for AB. So we'll have X in feet here, and we'll have M sub wind in kips. And our moment diagram, because we have a pin here at A, moment is going to start at 0. And remember, to get the moment diagram, the change in moment is equal to the area beneath the shear diagram. So we're actually going to have a moment diagram that looks something like this. And then it's going to abruptly close just beneath that 12-foot mark. And this is going to be our moment diagram. And this value is going to be equal to 36 kip feet. How do I know that that's 36 kip feet? Well, I can make a little note here. I can say the change in moment is the area beneath the shear diagram. So the change in moment is going to be 1/2 times 6 kips times 12 feet. And so you get 3 times 12 is 36 kip feet. And then the shape of this is quadratic. Okay. And so there's our maximum moment. Maximum moment is happening just beneath that 12-foot mark, or just at the 12-foot mark, but infinitely below the corner. And then, of course, we can have an axial diagram due to the wind load. So axial diagram for AB. Draw that a little bit better. And the axial diagram will just be constant, okay? So our axial diagram will be a constant value of 3.6 kips in tension. Again, you have nothing else that is generating an axial load in this vertical member other than AY, which is causing which is translating as your 3.6 kips in tension. So we're going to call this part 1 of this video, just so it's not super long. So we'll have a part 2 where we finish off this example and apply the LRFD load combinations. So follow up with part 2 right after this.